Cast is now starting. All attendees are in listen-only mode.
Hi everyone, thanks for joining. We're just waiting for other people to join, so we'll be kicking off really soon. If you've got any technical questions or anything, feel free to use the chat or the questions in your toolbar. Hello to everyone that's just joined. We are just waiting for some latecomers to join on, but thank you very much for joining, and we'll get going soon. Welcome to everyone that's just joined. We'll just wait 1 or 2 more minutes just for the last few people to join, and we'll get going. Right, I think we'll start then. So welcome everyone, thank you for joining. Welcome to our webinar. We're going to talk about smarter grids with power electronics. Just to introduce myself, I'm Olivia Carpenter-Lomax. I work for Ricardo Energy and Environment. I'm a principal consultant engineer, and I support lots of network innovation projects, and I'm going to be your chair for today. We're going to hear from two cutting-edge, really exciting network innovation projects currently underway within using power electronics. So we're going to hear from Luca Grella and Joe Colebrook from UK Power Networks, who'll tell us about active response and what they've learned about specification and design of power electronics within their project. And then we're going to hear from Ali Kazaruni and Chad Eckhart. So Ali's from SPB Energy Networks and Chad is from Earnco Gridbridge, and they're going to tell us about LVEngine project and the solutions being developed for that project. So after those two talks, we will then have a quick question and answer session. So if you've got any questions during the session, please let us know. And I will show you now, in case you haven't already worked it out, how to ask a question. You can do this any time in the talks. You don't have to wait until the end. So if you use the control panel that should be on your screen, either to the top left or the top right. If you can't see it, then have a look for the little green, little orange arrow, which means it will expand for you. And then click on the questions bar there, and you should be able to type your question in. And it'll either get answered during the event, or we'll try and pick it up at the end. And if we have time, we'll try and cover as many as we can. So before we start, we're just going to do a couple of polls. So the first one is nice and simple. Which organisation do you work for? This is just so that we can have an idea of who we have in the group. And hopefully you can see the options, DNO, university, public body, industry or consultancy. Click the one that applies to you, or the one that most closely applies to you. Just click on the little white circle. Right, we're getting some results in there. So we've got a few people from consultancy. We've got quite a nice spread actually between all of them, apart from no one from a public body, but we've got attendees from DNO's, university and industry and consultancy. So that's good. And then if we're ready to go on to the next poll, which is much more about why we are here. So what's your purpose for attending and what you're trying to find out whilst you're here? So is it to find out more about power electronics and their use in networks? Is it to know more about facilitating net zero using power electronics? Or is it more about the technical design and specification aspect of power electronics? On this one, by the way, you can click more than one. So if you're keen on multiple ones, you can click on more than one. And again, we have quite a good spread. We have lots of people interested in knowing more about facilitating net zero and about the technical side. And also a few people wanted to know more about power electronics in distribution networks. Great. So if we move back to the slides, hopefully you guys can see the slides again now. I can have a thumbs up from the other speakers, just so I know that's what you can see. Excellent, good. So let's get started with the first talk. I'd like to hand over to Luca and Joe to tell us about active response and the learning from the specification design of HV and LV power electronics within the project. So over to you, Luca.
Thank you very much, Olivia, and thank you very much also to Ricardo, for hosting us today. So, and thank you for all our attendees. So, just a little bit of introduction. My name is Luca Grella, and I'm the Active Response Project Lead. I'm part of the innovation team at UK Power Networks. And today, I'm not alone. I have with me, Joe Colebrook, one of my colleagues, actively working on the technical side of power electronics, which is the hot topic of this webinar. So I'll go through the presentation. Here we go. So today, from our side, you will find out a bit more about, first of all, the introduction about the project, Active Response, what we do, how we do it. Then I think what we all are here for, so the power electronic specifications from a DNO perspective, what is actually what we really need, what we believe we need from a DNO perspective, and then the architecture, the key challenges, takeaways, and all the technical aspects that will be covered by Joe later on. So, but first things first. So let me give you an introduction about UK Power Networks for those who are not familiar with us. So UK Power Networks is the distribution network operator of the southeast of England. We deliver electricity to almost 20 million of people. We have a peak power of roughly 16 gigawatt, and at the moment, as in the past, we are very, very focused on how we can deploy innovative solutions in order to avoid the costly reinforcement of our network. As you have seen, in the past, the uptake of low carbon technology such as electric vehicles, heat pumps, and so on is putting a strain on our network, and we are looking for smart solutions. And Active Response, the project that I'm actually leading, is one of that, and I'll give you some information about that today. So what is our Active Response? Active Response is an Ofgem, so the GB regulator funded project. UK Power Networks is the lead DNO, so and I'm glad to be the lead, the project lead of the project, as I said, and we are coordinating all the activities in collaboration with our partners. Partners such as SPB Energy Networks, Ali is a representative person today, but not only that, Ricardo, Energy and Environment for support in terms of engineering consultancy, Turbo Power System, the company that is delivering these devices for us that are facing incredible, very, very difficult challenges on this, but that are at the same time resolving them, and we'll talk about that in a second. So, and then we have CGI from a data management perspective, Nexant and Smarter Grid for network optimization. So as you can see, is a big partnership to actually solve this incredibly difficult challenge. So the project started in 2018, and the key objective is basically to demonstrate that optimization, automatic reconfiguration of the HV 11 kV and LV 400 volts networks can actually provide a lot of benefits to our customer. And that is in particular using power converters, power electronic devices, and we call them soft open points and soft power bridge. Both in the first one in the LV network and the second one on the HV network, and I'm going to talk about that in a second. The way that we have divided our project is in 4 packages. So number one, as you can see here from the screen, is about hardware. The second one is software. Third one is about project trials, and then learning and dissemination. Today I will talk about mainly work package 1, so about the hardware, where actually the key learnings are from a power electronic perspective. So why do we do Active Response? Why do we do these innovation projects? We have a number of benefits that we have in our business case. Network flexibility is one, network control, but the most important one is about the network enforcement deferral. So we want to try to use as much as we can the spare capacity which is in our network. And to do that, we need power converters, power electronics. The project will deliver 9 reports, and these reports will focus on, selection criteria, where to put these devices, how we should operate, how we should install them, what is difficult in terms of specification, design, and testing, and so on. And you can find them on our innovation website. So if you want to know more about these devices and the learnings, please go also on our website and you will find the report. So far, 4 of them, they are published, and then in the next few months you will publish more. If I move on now, so the trials. So what are we actually going to do in the project? So we have divided the project in 4 trials. One is called Active HV, which is about network optimization in terms of moving the anomaly open point on the HV network. The second one is about the application of the soft open points, so the power electronic devices on the LV network, and the active reconfiguration of the normal open points on the LV network. The third one, what we call Primary Connect, is about the testing on the live network of the biggest power converter that we are going to install, so the soft power bridge, able to share capacity between 2 primary substations, and we're going to give you a bit more detail later during this presentation. And the fourth one is called Active Response, so everything in combination, orchestrated by an active network management system. But let's go to the juicy bit. Let's go to what I think we are all interested here. So from a DNO perspective, what do we need? What kind of device do we need in terms of power electronics to optimize our network? So what our answer from an active response perspective is soft open points on the LV network, and you can see on the left-hand side a kind of simple schematic, and on the right-hand side a high-level specification set. So what are these devices? So the soft open points, we will deliver 2 different types of power converters. One is called 2-terminal and one is called 3-terminal. The 2-terminal SOP is called like that, as you can see from the presentation, because it's connecting 2 secondary substations. The 3-terminal is connecting 3 secondary substations. The basic function is to enable the power sharing, so the mutual support between 2 or 3 primary, 2 or 3 secondary substations when is required, in order to when you have mutual, in order to release per capacity on our LV network when is required, particularly at different time of the day when the load is a different level on different part of our network. So one key specification on that is that the 2-terminal SOP is a street furniture, which is one of the interesting things of the device. So a lot of flexibility. You can put it in a pavement, and that will enable 2 secondary substations to help each other when they're struggling. So in order to refer reinforcement of one. The 3-terminal SOP will be an indoor substation installation requirement, so we will have that, so we can be hosted in a secondary substation or an LV only substation. In terms of power rating, we're talking about 240 kVA for the 2 terminals and 400 kVA for the 3-terminal SOP. Just to give you a bit of reference, the transformers that we have on a secondary substation are between 500 kVA and 1000, so quite substantial support that we can have from these devices. And then the fact that one of the most important things is the fact that we are going to use silicon carbide. So silicon carbide is the key material that the turbo power system they are using to create this excellent device. And it is a kind of a good challenge, very interesting, to use a different material, but the benefits these guys are delivering, they're quite incredible. In particular, from a thermal performance, so silicon carbide, they will give us the opportunity to provide more power, but without incurring in thermal issues. But at the same time, to use a switching frequencies that are much higher than conventional material. And this we are talking about 20 kilohertz switching frequency, which will enable also ourselves as a DNO to install these devices in places where it's most convenient for an electrical perspective, but without incurring into noise, which can disturb our customers. Another power electronic device, but from an HV perspective, so we're talking about 11 kV, is the soft power bridge. So conceptually similar to a 2T soft open points, but obviously installed on the 11 kV. So the substation you can see in this simple schematic, they are primary substation. So we are talking about 2 big primary substations that they will share load between each other without actually transferring fault current. As I said, the kind of power rating is 5 MVA, and with that rating, two primary substations will be able to sustain each other and defer the reinforcements up to that point, which in line with our studies, it can be up to 10 years of reinforcement deferred. Again, silicon carbide based device controlled by an A&M system, and everything will be orchestrated by that. I'll now leave you, with to Joe, that will talk about more about the technical aspects of that, and this is how we are going, how TPS in collaboration with UK Power Network has designed these devices, and the key challenges and key takeaways which are useful. And again, if you have any questions on this presentation, anything you would like to know, please feel free to use the panel on the right hand side and ask, so we will respond at the end of this presentation. Thank you.
Thank you, Luca. As Luca said, my name's Joe Colebrook. I'm an innovation workstream lead at UK Power Networks. So I'm working as part of the active response team, and my main job is to help Turbo Power Systems with the development of these devices, and then also work with our network operations team to install all this equipment. So I'm going to take you through some of the key points about the architecture of the SOPs and the SBB, and then some of the important things we've had to consider when installing these. So here on the first slide, this is the 2-terminal SOP. So this is just been built in TPS factory, and they're currently testing it at the moment. So what you can see here is, this is a back-to-back converter. It's connected to 2 LV feeders. So you've got an inverter for feeder A here on the left, an inverter for feeder B on the right, and then you've got a neutral converter in the middle. And you can't quite see it, but at the back there, the sort of red, where it's actually copper, there's a DC bus bar on the back of it, at the back. This has been built with with replaceable units in mind. So you can quickly swap in and out various parts of this. So you've got the inverter limb modules here that can be lifted out, and same with the neutral converter and the control cards as well. So it's been designed for that sort of quick maintenance in mind. The other thing that we've had to design it with is, it's got to be installed on a pavement, as Luca said. So it's got minimal width. So it's about 0.5 meter wide, which allows it to be installed on pavements. We've also designed it to make sure that it has, it's easy for our operations guys to install. So there's sort of the terminals down here on the bottom left, and these are the standard LV terminations that we use for various other LV equipment, such as cutouts. So that follows our jointing standards that we have. It's also had to be designed to work with these new 20 kilohertz silicon carbide devices. So as Luca said, they're very efficient, losses are a lot less, but to keep the noise to a minimum, we don't have any fans in the 2T SOP. Well, there is a fan, but it only operates at peak current, so very limited amounts of time. So the thermal management is a really important part of this design. Particularly inductors at 20 kilohertz have a lot of core losses, so they've had to be specially designed to limit those losses. And lastly, there's a connection to our remote terminal unit. So there's a local RTU for this device that will be if I go to the next slide, it's here, and that connects to our SCADA system. So just to give you an idea about a couple of, when you install this, obviously it's on a pavement, so we've had to get permission from local authorities. Generally, we can install it in the same way you install a BT cabinet, and you get what's called permitted development, which means you don't actually need planning applications, but that may vary between different local authorities. An important point to note here is that, as Luca said, there's 2 link boxes that need to be installed in front of this. That allows you to then bypass it if you want to just operate the network in a radial system. But then when you do want to use the SOP, you need to be able to connect each feeder separately to the SOP, so that it can share power between the 2 without transferring any fault level. And lastly, this has been designed to make sure there's no electrical connections or anything exposed, so that the public are safe. So if I go to the next slide, this is the 3T SOP now, very similar as a design, and has got all the same modular components as a 2T SOP, which makes build very easy. So you've got the inverter A, B, and C. Now this is a 3-terminal SOP, so it connects to 3 feeders. You've got the neutral again, the bus bar behind it, control cards for each one. So again, all replaceable units. Now, this is also a modular installation, because it needs to be built in an LV substation or a secondary substation. So each of these cabinets splits into 4 different, so it's 4 sections, and they can all be then brought in through a door. So they're designed to fit through a substation door, which makes transportation easy. An important point on the 3T SOP, which is very different to the 2T SOP, is that it needs to connect to an LV board. So when we're designing the site, if you see here, and these are some pictures which kind of show how we're going to connect it to the LV board. So it's going to be, it's got to connect to 3 different ways on the board. So we've tried to keep it, again, as easy as possible for our operations team. So it follows a similar design to how we connect temporary generators. So you have a separate cable for each phase, and then one for the neutral, and they connect onto the bus bar using these Lytton connectors and fuseways like this. Now, when you have it in a substation, you're then going to have you need to make sure the cables are out the way, so there's no hazards or trip hazards. So we're going to be using cable trays like this round and then onto the bus bar. So we're hopefully going to plan to install these in the next couple of months. So I'm conscious of time, and so I'm going to go on to the SPB architecture. Now, I'm not going to have enough time to do this design justice, but I'll kind of give you an idea of what we've got here. So the SPB is very different to the SOP. It follows a sort of unified power flow controller architecture. So it has 3 voltage source converters, which allow us to transfer up to 5 megavolt amps of power from one feeder to another. But at the same time, you only have to rate the converters for 1 MVA. So these 3, they're actually 3 converters all at 350 kVA. And this allows you, again, the equipment to be much smaller and therefore hopefully easier to install in more places. Obviously, because of this, the converters being at 1 MVA, you've got you're limited in operation by the voltage difference between the feeders. So because of that, ideally you want to place them somewhere where you've got sort of similar voltage either side, and then similar impedance. So, for that reason, we place them at secondary substations, and this being a first of its kind device means that, there are some quite tricky space constraints that we're having to deal with for this device. But as I say, this is a first iteration of this device. So when we're placing it here, there's quite a few important things to think about this architecture and why we've created it like this. Mainly for safety reasons. So, safety is our #1 priority in UKPN, and we've had to set it up in a way that it's got, lots of protection, and that we're complying with the distribution safety rules. So this is all of this system is considered an 11 kV system. Even the converters, which actually operate at 1,000 volts, the whole thing is 11 kV. So we've had to make sure that it can be earthed at all points. So the RMUs are earth switches, and then we've had to add in these earth switches here next to this isolating transformer to provide, when there's maintenance, we're able to earth it. I should probably point out, so the way these converters work is they float on the voltage between each feeder. So they're essentially floating on the voltage, and therefore they're insulated from ground. So they float at 1,000 volts, but it means they're not grounded in any way. So when you do need to maintain them and work on them, you need to make sure that somehow you can earth it to be safe. So yeah, and then the last bit really is to talk about here is the interlocks. So again, to prove the system is dead when you're working at 11 kV, you need to prove everything's dead. So we've got these mechanical interlocks, and there's a couple of different energy supplies. So obviously you've got each feeder, but you've also got this LV supply, which is used to charge the DC bus bar when it starts up. So it's very important that we've got these interlocks in place to make sure that no one can access the building that this SPB is in when it's in operation, and that actually includes commissioning as well. And just to maybe, so everyone's, this HV switch, you're probably wondering what this is. So due to the design, we need to make sure that fault current isn't being transferred from one side to the other. So this HV switch is a very fast operating switch. It operates in about 10 microseconds, and that makes sure that if there is a fault on either side of the network, externally to the SPB, that it trips out this and actually sends an intertrip to the two RMUs. And therefore limits the current. Because it operates so quickly, it limits the current that's the fault current to around 350 amps. And then lastly, before I finish, I just want to show you sort of what we're trying to, how we're installing this SPB on site. So this is our Wormley Wood substation. And here you've got the existing site at the moment with its you've got an LV board and some transformers here at the top. You've got an existing empty building here. So all of the extra switch gear that I just described and transformer is all going in this existing building, and then we're building a new building here to have the SPB. And then here at the bottom, because the SPB is a water-cooled device, it's got a radiator. So yeah, as I say, one of the key challenges really with this is space, and there's not going to be it's difficult to find somewhere where we can fit this in at the moment. So this is the Wormley Woods, and the last thing I guess to mention here actually is that we've had to be very careful about the noise of this radiator, because we're in a residential area. So we've had to make sure that it's not too noisy to disturb any neighbors and cause any issues. So I'll leave you with a picture here of a rendering of what our substation is going to look like with the SPB. So as you can see, the top one there is what originally, it looks like at the moment, and at the bottom is what hopefully it's going to look like when we've installed it. And as you can see, it shouldn't have too much impact even in a residential area like this. So I think I'm now going to hand back over to Olivia, who's going to introduce the next project.
Thanks, Joe. Really interesting, really interesting presentation from Joe and Luca there, and some really practical aspects coming out of that project, which is fantastic to see. So as I've mentioned already, if you've got any questions, we're going to handle them at the end. So please get typing, and I can see some questions coming in already. So we'll try and handle as many of those as we can at the end. In the meantime, if we move on to the LVEngine project, and Ali and Chad are going to tell us about the LVEngine solutions and products and the design challenges. So just to hand over to Ali, please.
Thank you, Olivia. I just happen kind of to have a camera issue, and they say kind of my camera cannot run for some reason. But there you go. So good morning and good afternoon, everybody. My name is Ali. I work for SPB Architecture Networks. I'm lead engineer, and then currently kind of engaged with several innovation projects where I am technical lead for them, and one of the most important ones for me is LVEngine. So which we're going to talk about today. So with me here is Chad Eckert, our from GridBridge, our project partner. I pass it to Chad while you're introducing yourself. I can try my camera again, Chad.
Sounds good. Thanks, Ali. Glad to be here. I just a little bit about myself. I had a decade working with large equipment manufacturers, all focused on electrical apparatus. And 10 years ago or so, I founded a company called GridBridge, which is focused on power electronics and electrical networks. That organization was acquired by Armco in about 2017. And we'll talk a little bit about that. There's a couple slides later in the presentation. Today, I lead the organization that I founded, along with some operations and the strategic planning process for the parent organization. So I can say that this is a high priority project for us, and looking forward to sharing some of the details in this presentation.
Great stuff, Chad. Thank you very much. So unfortunately, kind of I have to go ahead without camera for some reason. So as I mentioned, in the next 20 minutes, hopefully, kind of I'm hoping to give you some awareness about LVEngine projects, which is a sister project with Active Response. Basically, we're very closely working together, doing activities on the LVEngine. Chad is going to kind of provide some instruction about his organization, which kind of is the most important partner we have on the project currently, and then hopefully kind of give you some flavor in terms of the journey we have gone through, the product we're going to develop, and the lesson learned we have had so far, basically, and tell you what's going to happen next, basically, in our project. So for those, I noticed kind of people coming from different background. For those who don't know SPB Architecture Networks, we are distribution network operator in Central and South of Scotland, North Wales, Cheshire, and Merseyside, and also kind of we own the transmission network in our Scottish patch, basically. So we keep the light on for 3.5 million customers, and for that we have to kind of manage our assets, which spread kind of at transmission and distribution level, over 100,000 kilometers of overhead line and underground cable, and more than 30,000 substations, basically, at transmission and distribution. So being a kind of DNO, being in the UK, and as you know, kind of the running innovation project is very important for us. Basically, all of the kind of DNO facing a challenging time, as Luca and Joe mentioned, in terms of kind of the way we consume energy and generate energy is changing. So we just kind of need to prepare kind of our network. So we have a portfolio of over 150 million pound over kind of last 8-9 years, kind of to run on innovation. And LVEngine is one of the flagship projects, basically started in 2018. So we have several kind of partners on the project. Chad and Armco GridBridge, one of them. We have University of Strathclyde, Keele University, of course, kind of UKPN as a project partner from TNO side on board, basically, and there are other kind of bigger team in terms of contractors and consultants, etc., on board as well, including WSP. So what we're going to do with LVEngine? LVEngine is basically targeting about application of power electronic within secondary substations. So we're going to design and trial solid-state transformer within secondary substation. And with that, we're going to bring some flexibility and controllability in secondary substations. So that includes the control voltage per phase separately and LV bar basically, and we are planning kind of to use the smart meter data to inform this control voltage activity. We are planning kind of to do power factor correction and cancel the imbalance load we see from LV network, so HV doesn't see any imbalance load, and also kind of provide power flow control at the substation, which kind of can help us by closing interconnection between two neighboring substations, sharing capacity between two neighboring substations. LVDC provision is another aspect of our project, basically. So you can see it's quite a move from what we are at the moment as a passive secondary substation to something very, very active. So there are two main products we're going to have in LVEngine. One is a power electronic unit added to the existing conventional transformer. I would say existing, obviously going to be a bit of change, but it's going to be connected through the cable to the conventional transformer. It's a UPFC kind of topology, which by injecting voltage basically to the main supply from the secondary side of transformer and manipulating the voltage and phase can provide kind of the control we require. Obviously kind of there are rectifier etc. to provide racket power and imbalance load cancellation basically. And obviously kind of with this conversion we have DC link, which can give us kind of the DC supply we require. So the other product we have is full power electronic transformer, which starts from HV side basically, where we're going to use 2 kilovolt silicon carbide modules basically to connect to the HV network. Is very challenging kind of aspect of the project because most of the power electronic units, as is still down, and then kind of they do all the conversion. But the whole topology we're going to have here is a typical 3-stage solid-state transformer where you convert AC to DC from HV. You have a DC to DC with a galvanic high-frequency transformer basically integrated in that, and then the last stage DC to AC, and obviously kind of the DC output basically as one of the supply point for the unit. So I'm just going to kind of talk about more about the first product, hopefully kind of to not take much of time of this presentation. But I would pass first to Chad because they are helping us kind of to develop these products, and we have been very closely working with each other since kind of almost a year and I would say kind of 3-4 months, Chad, now. So pass to you, Chad, just a bit of introduction from your side, and I carry on then. Thank you.
Yeah, great. Thanks for the handoff, Ali. Yeah, it has been over a year at this stage that we've been working together on this program, and just 2 slides to share a little bit about ERMCO and ERMCO GridBridge. ERMCO is one of the largest developers and manufacturers of distribution transformers or service transformers and components in North America. And so the organization's about 50 or 60 years old at this stage, and it's owned by a group of electric utilities. There's 4 locations, all focused on the central and the eastern part of the United States. And from an operations standpoint, it was about 140,000 square meters of manufacturing. There's a picture on the top of the screen that covers some of the operation, not all of the operation. And that operation really covers about 18 hectares or 45 acres of land. And so there's again a massive operation, a massive aspect of ability to perform and service utilities throughout North America, and as we expand throughout the global footprint. One of the things that's very interesting is Armco acquired GridBridge, a company that I founded in 2017, and really that structured one of the only equipment manufacturers whose core focus it was to have a transformer and power electronics solution from start to finish. And so it really positioned us well because, you know, the work that we're doing here is in the core roadmap of Armco GridBridge, so it aligned perfectly with the organizations. Next slide, Ali. GridBridge has a history prior and was formed in 2012. Some of you on the call may be familiar with the Freedom Systems Center, which was a Gen 3 ERC that was focused, or that was funded by National Science Foundation. There were 7 universities involved, and I believe 5 of those universities were in the United States. 2 of those universities were overseas, and so some of you on the phone may be familiar with that. GridBridge received early support, certainly from National Science Foundation, the Department of Energy and Department of Defense, to focus on power electronic solutions for the electrical network. And really, you know, that's always been our focus. You know, we've served as a pioneer in that space for the grid for, you know, coming up on a decade now, which time flies when you're having fun. And I got to say, some of the products that we've put out in the field have been commercially available, and since you know 2014, 2015. So one of the things that we've been able to do, since we've had a great deal of field experience, is pull on that field knowledge. And you know, there's been some unique requirements that have been part of this program, and we've been able to leverage some of that field experience with power electronics that we've had, and so that's been great. And a picture of some of the you know, early products that are Armco GridBridge focused are on the bottom center of the screen, and Ali will talk more about the product that we're releasing as part of this program, or the LVEngine program. Really most important here, and I think one of the reasons that we're so fit to be, you know, great partnership here is we're really working from inception to scaled manufacturing, as you see through these 2 slides. This is a new product with a lot of new requirements, and we'll be able to take that into product throughout the pilot stage, and then scale it into you know, wide scale manufacturing. So with that, Ali, I'll hand it back to you. This is just a quick introduction on the organizations.
Thanks, Chad. So that's great. You know, Chad mentioned in terms of kind of collaboration. One other thing I thought, you know, it would be good for this kind of, you know, presentation, and just kind of giving a sense about power electronic products development, is the fact is there is not kind of, you know, much of experience or kind of, you know, knowledge within the DNO world, basically, kind of about power electronic. And power electronic itself is a multidisciplinary effort, basically, you know. So when you run the project based on power electronic, the 2 aspects of the project, which is project inception, is the most important aspect for me, you know, because all the people coming around the table in terms of the power electronic manufacturer, the power system people, protection people, IT people, mechanical engineers, they need to just get it kind of understanding exactly what are the kind of, you know, limitation of the product and trade-off would be, you know. Although the DNO, in the DNO world, you provide kind of a technical specification you want, but that aspect is very important. And if I kind of just want to share the lessons, because many people think about that in academic world and then other kind of, you know, organization. When we started for kind of, you know, having power electronic added to the conventional transformer, we started with a back-to-back arrangement. And that ended up to be kind of, you know, a difficult kind of product to get together in terms of cost, reliability, et cetera, whereas we will move on to kind of the UPFC arrangement, where kind of you don't need to transfer all the power to the power electronic unit to supply the customers, basically. And there's a power electronic kind of unit although it's sitting in a series almost with a transformer, but just have the kind of direct pass through basically routes. So and then just provide the services. So we significantly improved efficiency we wanted, and by that kind of and also kind of the price end up to be much less, and the thermal management is not going to be was kind of much less difficult kind of to manage, and that became our product basically. So in terms of to see how you want to kind of how it look like is a kind of unit. Basically, it's going to be a cable connected arrangement to existing transformer. All terminals, again, kind of we wanted in a way to be very close to our existing kind of termination arrangement. The unit should be small. It's just it's 1200 by 1600 basically height. So it should be fitted within the secondary substations, and also kind of interface with that, where we can get kind of Ethernet port to our secondary RTUs, and also some testing point to make sure kind of when the unit is de-energized, our staff are kind of testing internal voltage, because that is power electronic and DC link, etc. You have kind of the internal charging basically still there. So that's been provided to make sure kind of health and safety kind of aspect is covered. Joe mentioned about health and safety. There's a big deal about that, to making sure kind of how this unit can be safely operated, can be safely kind of disconnected from the network, and can be kind of, there's a slide on the protection side. I'm going to take you through that as well. So the targets and what we have designed so far is a maintenance-free arrangement, is a closed-loop kind of water cooling. The weight is 1500 kg, which is not kind of very light, and the most weight coming from the 3 coupling transformer you see in the design here, basically. So one of the things I was going to share with you is the service priority. When you design a power electronic, basically what we have here is a 500 kVA unit connecting at a nominal voltage of 400 volts, basically. So the voltage control we can provide is 16% boost or buck, means 16% of the voltage we're getting at the LV terminal can kind of be increased or decreased, which is 37 volts basically for each phase. And then the DC power of 150 kilowatts at 950 volt DC. So the imbalance load can be cancelled up to 30%, and the power factor correction 0.9 bleed or lag to unity. But the fact is, you don't need all of them at the same time. So it's good kind of to consider when you design a power electronic unit, to see if you hit all of kind of this requirement, what function might be kind of gradually reduced, not drop completely, but gradually. Decide kind of do the imbalance load cancellation first, and then power factor correction next, basically, if we see any kind of overrated issue with the unit. One of the most important thing of this unit is the protection. So the unit is being protected kind of by a fuse, and that fuse kind of should be in coordination with what we have on our main unit, and also kind of on an LV AC board. But also this unit should be kind of protected when a fault happens, basically. So there's a high current going through kind of this route, which can induce high voltage on a secondary side of or primary side of the coupling transformer. So there's an element here which is very important part of this protection scenario, which is solid state relay here, which can bypass our coupling transformers when it sees kind of high current going through that. That's also can be used as an operational kind of scenario when you want kind of to bypass the whole power electronic. So you see kind of the solid state relay should be kind of somewhere. The fault level withstand of that is just or the thermal capability of that should be above kind of the fuse we have at this point, which is 800 amp fuse. So I'm just going to wrap up. I noticed kind of there are different kind of people with different backgrounds on the call, so in terms of challenges, kind of there are two things I would sort of leave you maybe kind of, on an industry and academic side kind of can think of about, which we have dealt with to some extent, is how do you kind of, if you remember, we're going to interconnect this unit with some kind of conventional transformer. How are you going to the transition between a mesh arrangement to radial arrangement? When you talk about power electronics, you talk about voltage control or power flow control or grid following arrangement. So that's a challenge. How you transit between this. I think we kind of nail it in this project, which we are kind of we're testing it now. But most of the power electronics at the moment are grid following. And we kind of think of kind of grid forming basically power electronic control when we have connected to a mesh arrangement. That's a very kind of hot topic to me, and it's good kind of develop kind of some solutions for that. So the other thing is temporary overloading capability. To 1 second, 5 seconds. There's nothing for power electronics, obviously, but if you kind of want to have overloading capability for the fault scenarios or for kind of some sudden change in load, so what you have is basically kind of you use higher rated kind of power electronic. But can we use some techniques to survive 1 second, and not adding more modules to our power electronic devices? So that kind of help us to reduce the cost, increase the reliability, and also kind of make the size smaller, because it's very important. Joe already mentioned how important the size is to fit it in our limited space solicitation. So the key target for us coming year is to finalizing this prototyping. Design is finished, and then start the factory acceptance test, and hopefully kind of bring the unit to the site and install it in our trial site we identify. So apologies, I'm just 5 minutes over time, but thank you very much for listening, and then hand it back to Olivia to take us through to the question session perhaps.
Thank you, Ali, and thank you to Chad. Another really interesting presentation. So just whilst the speakers are bringing their videos on ready for the Q&A. I'm aware that we are running low on time, but we'll try and squeeze a few in. Just if you do want to ask any questions, just remember, go into your control panel and ask the questions there. So if that's all right with you, I think we will start with a couple of questions for active response, and then we'll do a question for LVEngine, and maybe wrap up with an overall question at the end. So we've had a couple of questions in very specifically to do with active response. One is to do with the earthing of the SOPs, and I know, Joe, that you talked a bit about the earthing of the SPBs. So this is just a question about the earthing arrangements for the SOPs and what that looks like. And there's another question about why the IP ratings of the terminals needed to be different. So a couple of quite technical questions for Luca and Joe. That's okay?
Yeah, shall I take the first one, Luca? So on the SOP earthing, so the 2T and the 3T SOP, they have a T, N and S system. So the neutral terminal is connected to the earth system, and then the whole earthing inside the SOPs are connected to the substation earth system. Luca, I'll let you answer the IP one.
Yeah, no problem. I've seen a lot of interesting questions. So, for all the questions directed to active response that we cannot cover here, I will respond separately. We will respond, via email and come back to you. So regarding the one on the IP rating, obviously we have two different, devices. So we have the 2T SOP is a pavement mounted because it's a slim, is a quite flexible device. So we can put it outside. Therefore, the IP rating was superior. And for the 3T SOP, because of the size and the fact that we will have an extra leg, is not so handy to put it on a pavement. Therefore, needs to be indoor. And the fact that we can put it indoor, we wanted to relax a bit of the specification on that to make it easier for for design testing and installation. So there was not that strict requirement. And I will hand over to Olivia.
Great, thanks guys, and thanks for the quick responses as well. So the question on the LVEngine project is a question about the DC link and why the choice of the voltage level on the DC link rather than a more standard option. I don't know if Ali or Chad is the best person to answer that.
Sorry, Olivia, I don't know if it was just me or everybody else. I lost the first part of your question. Can you ask it again, please?
That's fine. So the question is why the choice of 950 volts for the DC link rather than a more standard 750?
So that's very interesting when you say 750 is standard, because there is not much kind of opinion about kind of why is a standard LVDC public network for voltage per LVDC public network. So when we pick up 950 was first kind of naturally in a DC link we get to 800 volts. So within the power electronic, when you design it, basically, is basically you're getting kind of the best kind of internal DC is 800 volt basically. And then we consulted with a partner we have on the EV charger, because in our project we're going to supply low voltage DC to DC fed EV chargers, 150 kilowatt EV chargers, ultra rapid. So that's a consultation happened, and based on kind of the voltage they're getting at the car, and so optimization of the kind of EV charger unit itself, they suggested to go for 950 volts basically. So 800 volts and 950 volts basically just a combination of came out from this exercise. I don't know if it makes sense or not.
Thanks, Ali. Just one question, I think, for everyone, if we can try and give one succinct answer to this, putting you all on the spot here. What do you wish someone told you about power electronics and getting involved in power electronics projects for distribution network before you started? Just if you
I can try to answer that. At least I can answer from my point of view. So I think is the difficulty on the interface. Obviously, the world of power electronic is a world on its own. The components, the different modules, and having that in isolation is one thing. Having that working well in a complex environment such as a distribution network is even a greater challenge. And I can see that all our engineers, from a project perspective, but also the partners from a TPS perspective, are actually working hard and working well to find solution, because this challenge is not a trivial one.
I'll go next. It's definitely the degree of coordination with traditional equipment inside the grid. There's challenges that we're faced with when we're working with traditional analog devices and not solid state devices upstream and downstream of the power electronics.
Yeah, no.
Yeah, maybe. Sorry.
Go on, Ali. Go on, you go.
Sorry, Joe. So I think I echo what Luca and Chad said, but as a personal kind of view as well, I always saying that when you start a power electronic product development, as a DNO, what we do is look at kind of the ideas, what we can do, specifications, read papers, etc., yeah. It's always kind of very difficult to say that how much of those academic and research paper can be turned to real products. Yeah, I think that knowledge, if we can bring together at the beginning as a DNO and just inform us basically, is great to have. That's something I would say kind of something before starting a power electronic project I would appreciate to know. Sorry, Joe, pass to you.
Yeah, no, I guess mine's similar vein as everyone else's. You know, I would have liked to have known that. I guess that I would have to have become, be able to explain it in very simple terms to people, particular other people in our company that are going to use this equipment, at 3 a.m. in the morning when there's a fault or something. You need to be able to clearly explain how it works, and often with power electronics that isn't easy because the theory behind it, isn't quite as easy as standard distribution electrical theory.
And we see Ali right at the end.
That's what eventually.
Okay, we are a couple of minutes over, so I think we will finish there. Just to say thank you to all of our speakers, to Luca and Chad and Joe and Ali. And of course, thank you to the attendees, those of you who have stayed even a couple of minutes late. Thank you very much, and for your questions coming in. We'll be sending out a feedback form. It's really useful for us to understand how you found the event, so please do respond to that feedback form, and the slides and recordings will be made available. And other than that, I think watch this space. In the email with the feedback form, we will give you contacts for Ali and for Luca if you've got any questions beyond the ones you've asked, and also a link to the websites just to do any more reading, and absolutely watch this space for more events like this in the future. Yeah, thank you everyone, and goodbye.
Thank you.
Thank you.
Thanks everyone.